So in this video, I'm going to be talking about a qualitative technique. We just got done talking about last week about quantitative, and the technique that we use is the separating of variables. And we were able to, from that, come up with some fairly precise equations in some situations if we were given an initial condition, and also to come up with some general equations, or well, a general solution that represented a whole family of equations. And so we're gonna do this is another technique for solving differential equations, but it's called the qualitative because we're not going to necessarily come up with equations, but we're going to get, this is more of the geometric approach. We're going to be able to kind of get a picture of what the solutions look like. Since it's geometric, as I said, it's a geometric approach. That means we're going to be doing some graphing and kind of looking at what the solution may look like, or what the possible solutions may look like. So, and again, the term is called slope fields. So what we're going to be doing is drawing some slope fields. Now, some of you, if you had AP Calculus, I think that, I don't know if they do anymore, but that used to be an emphasis on the AP test. So some of you may have been exposed to this, and some of you may not. So the idea is with a slope field is, let's say we have a differential equation that's made up of, it's dy dt equals some function of t and y, and let's say that y of t is a solution. That means that we know that y of t, if we were to graph it, passes through, passes through the point t sub 1, for example, y sub 1. So again, if you think about what the function y of t is, you know, if I plug in some number in for t, it's going to produce some y. And so this is the notation saying, if I plug in this certain t, and we're using a subscript to indicate it's a certain one. So if we plug in t sub 1, then it's going to give an output of some special, you know, some specific y value. So what we're saying is that if this is a solution to that differential equation, then it's got to go through you know, a certain point. I got bugs flying at me here, sorry. Where y of t sub 1 would be equal to t. Would be equal to y sub 1. So this is just some basic algebra. You know, when you plug in a t value, you plug in a number for your independent variable, you get out a number for the dependent variable. And so then, this is the key part here. Then we know, if this is true, we also know that dy dt evaluated at t sub 1 would be equal to f of t and y. So referring back up to this function, f of t sub 1 comma y sub 1. Okay? So in other words, if I wanted to know the specific slope at this point, I could take this x value and that y value and plug them into my original differential equation, and it will give me the slope at that point. So that's what we're saying here. This is the Leibniz notation, where if you want to evaluate this derivative at a certain point, we indicate it by doing like this. And actually, we're using the x and the y coordinates, so probably the proper way to do this would be to say t sub 1 comma y sub 1. But anyway, the point is that we can generate the slope at that point by looking at the differential equation. And likewise, if I want, it's also true, if come up with some other point, like for example, t sub 2 comma y sub 2, and that would mean that I plugged t sub 2 into the into the y function, and I got out y sub 2. So if we wanted to evaluate the derivative at that point, then again we could just plug into the formula up above, plug my t sub 2 and my y sub 2 into that formula, and it will give me the slope. So if you remember back in Calc 1, we talked about tangent lines, and the derivative is the slope of the tangent line. So you can see that if I pick some random point off of a function, the y function, and I know the slope at that point, then that gives me a small little picture of what the graph looks like. And then if I pick another point, like right here, and I find out the slope looks like this, and then I pick another point, say right here, I find out the slope looks something like this. So if you get enough of these, you can basically begin to see some flow patterns of how the graph of the function might go. So let's look at an example. We'll pick a dy dt is equal to, say, y minus t. So here's a differential equation that involves both y and t. Now notice this one is not easily, well, it's not separable. In other words, it would be hard for me to get, would be impossible for me to get y and t by itself with y on one side multiplied by dy and dt on the other side, because if I subtract y from both sides, then I get negative y plus dy dt, and if I divide by dt, or if I multiply by dt to get it on the other side, it's going to show up over here. So this is not this differential equation is not separable. So our old technique, separation of variables, is not going to work on this. So we need some other way to access it. So the suggestion is we're going to try this slope fields. So what I'm going to do is draw a quick little xy plane here, and I'm going to start just generate some points. So we're going to say, okay, what happens at the point 1, -1? Now I don't know if that point is on my solution, because we don't know what, because remember we're looking for a solution y of t. I don't know what that function is, but I'm just going to say if this point was a part of the solution, I could calculate the slope at that point. So what I'm going to do is kind of like we used to do the x, y, t charts, or the x and y, t charts. I'm going to pick out a point, and I'm going to calculate the slope. So in this case, the slope would be -1 minus 1, which would be -2, like that. Okay? So now I'm going to go ahead and graph that. So if I go to the point 1, -1, that'd be over 1, down 1. So I'm talking about that point right there. And this is saying the slope of that point is -2. So I'm going to draw a short little slope line that's approximately a slope of -2. Okay, so then I'm going to grab another point. So -1, 0, and I plug -1 in for t and 0 in for y. So that would be 0 minus a -1, which would be just 1. So again, I go to -1, 0, put a little dot, and it has a slope of 1. So I'm going to draw a line that's approximately over 1 up 1. All right. And of course we can keep doing this. We'll do one more here in front of the camera. So -1, -1. And if I plug that into the equation, I get -1 minus a -1, which would be 0. So at the point -1, -1, the slope is 0, or flat. Okay? Okay, so I paused the camera and filled in some more because I didn't want you have to sit there while I'm doing all this. But you can do these things. All we're doing is taking the x and y, or the y and t, and plug it in to this expression up here to get the slope. So I'm going to go ahead and graph these now that I have them. Let's see, I've done the first three. So 0, 1 over 0 up 1, that would be right there, and the slope is 1. So it's in line with that right there. 0, 0, it's flat, so I put a little dot there and I draw a line. 0, negative 1 is right there. That's a slope of negative 1, so it looks about like that. And 1, 1 would be right over 1 up 1. That would be, oops, sorry. 1, 1, that would be 0, so that's also flat. And I did a few more off camera, so we got this one here, I think was 1 if I remember right, and that one there is a positive 2. So you can see with this one, of course the differential equations get more complicated, but it's not too bad generating these slopes values. So the point is, you go you find the point on the graph, and then you just draw a short little tangent line that represents the slope. And if you draw enough of these, you can get a picture of how the slope might flow. So I'm going to hop over real quick here. Did some on Desmos, so you can see a bigger picture of it. So you can see here's the let's see, I'm going to close that up. So you can see we're using that same one we had before. This is dy. We use x instead of t, but it's dy dx is equal to y minus x. So it's the same function, and you can see we just did a little grid right around the origin, but you can see this is giving you a negative 10 to 10 and negative 10 to 10 grid, and so you can see that a much better picture of what this looks like. So, and the way what this tells us about it, so in other words, we can start somewhere like this. Let's say that we know the point, well, this one is already there. Let's say we know that the point 1, 3 is on the graph. So if we wanted to roughly sketch this thing out, notice that if I go in the same direction that the little line is pointing, at some point I'm going to get up here and notice that this is saying that it's not as steep as it was. So and if you just kind of keep tracing, I hope you can see my arrow here. If you keep tracing it, you're going to follow these slope lines, and of course, when we follow this slope line, it sends us to a place where we don't see anything because we're only doing it every one. But you can get a picture of where it is. We're going to kind of keep going in this fashion, and so you can see that this thing is going to go something like that, possibly. And as you go back this way, looks like it's going to head down and hit this line. Now, if we hit this line, notice it's just going to cruise along right along that line. So, so again, this gives you some flow patterns, and there's a bunch of different solutions represented here. Because if I start somewhere else, let's say I start right here, well then, as I go to the right, obviously the slope of the graph is going down. As I go to the left, it seems to be going up, and I'm just trying to follow these lines, and eventually I hit and it tapers out, and it must, so it looks like maybe there's some kind of an asymptote going on here. But so anyway, this is it gives you a pictorial view of what what the possible solutions might look like. And we're going to play around with these slope fields. So the first thing you want to get good at is being able to generate them by hand, at least on a small scale like we just did, so you know how they're made up. But then also I would suggest that you go to Desmos and play around with it a little bit also, because it's also helpful to be able to throw a differential equation into the slope field generator, and it'll produce real quickly a picture like this. And by the way, I'm assuming most of you are familiar with Desmos. If you just go into Desmos and search for slope field generator, this thing pops up. There's a pre-made one in there. So anyway, I hope this will get you started on the idea of slope fields, and just kind of begin playing around with it.